I like that jacket. It's cool. I like that jacket. Okay, who's ready to do some of the most complicated stuff all semester? Okay. A few sarcastic nods, one honest no. Fine by me. How are we all feeling so far with translations into predicate logic? Okay, I mean, it seems like a little bit uncomfortable, right? I mean, it's hard stuff. It takes a long time to get used to. But I kind of hinted last time, and this is something we're going to get into over the last 2 weeks of class during Dead Week, is the notion of identity. But I just wanted to give you a hint of that, because once you understand what you're doing with this, you don't really even need the textbook. It's so simple. But so I showed you like the formula. You can add in x equals y, right? Last time I showed you a little preview. All this says right here is whatever x is, it's the same as y, right? So if I say Pierce is the same as the teacher in front of the room right now, right? And those are lowercase. They're just saying I'm the same as the guy in front of the room, right? Okay, so let's say if Pierce has a property and the guy in front of the room has a property, or let's say if Pierce has a property, if I am actually the same as the guy in front of the room, doesn't that guy also have the property? Right? Or I guess I could put it simply, if you and you end up being the same person, and I know that you're wearing a hat, doesn't that mean, not he, but you would be wearing a hat, right? If you were actually the same person. So if I could establish that there's identity between two subjects, they have to share all the same properties, because they're the same thing, right? The classic example is Superman and Clark Kent, his alter ego. If I could show you that Clark Kent has some properties, then Superman has to have too, because they're the same thing, they're the same person. So just real quick, if I say that P equals T, and P has, let's just say, a property F, then I can conclude that T has a property F. Does that make sense? Okay. And you can just stick these identity claims into whatever formula you want. They're their own little chunk, right? So if I were to tell you, I have a cat that is fat and is white. How would I say that? I have a cat that is fat and white. Or maybe I'll say it like this. I have a cat that is fat and a cat that is white. How would I say that? So let's just say we're not talking about a particular cat, right? We don't know which one it is. We don't know how many I have. So it's going to be a generalization. So I have a cat. Maybe I can simplify it further by just saying there is a cat that is fat and there is a cat that is white. That's simple. How would I say that? Any ideas?
You do existential.
Good. So there exists an X such that what?
Such that X is a cat and X is fat and X is white.
Okay, so there's one try. If I say this though, I'm presuming that this is all the same animal. There is at least one thing X that has all of these properties. It's a cat, it's fat, and it's white. But I just said there is a cat that is fat and there is a cat that is white. Now maybe they're the same cat, but I can't just presume that they're the same cat. Does that make sense? So it has to actually end up being there exists an X and there exists a Y such that X is a fat cat and Y is a white cat. Does that make sense how I'm now saying there is a cat that is fat and there is a cat that is white? Okay, we don't know if they're the same. Now, what if I wanted to say they're actually one and the same cat? It's my cat. It's just one cat I'm talking about. Well, then I just add on to this and X equals Y. That shows you, I'm talking about one object. There exists an X and there exists a Y such that X is a fat cat and X is a white cat and Y is a white cat and they're really the same thing after all. Does that make sense? So that means if X equals Y, I can conclude that they all have the same properties. And from this it follows that, there exists one cat that has all them. I can present that. Anyway, I wanted to give you a preview of that because I never really get to do it justice in a full semester because it just kind of crammed in at the end. But we'll have our own homework problems on that. So if you don't understand what I'm doing, not a big deal. Put that off for a few weeks. All right, any questions so far on homework or anything else before I start into really new material? Anybody have a hard time with anything we need to go over?
I don't really understand when you start adding like what you just did with like the x and the y. I don't understand when you add like
The second
modifier.
quantifier. Yeah, so it's kind of a skill you have to learn to parse them. I'm trying to find, the book covers it in, let's see, does it devote its own chapter to it? Did I assign 8.6? Does anybody know? I'll have my reading schedule if not. You can pull it up though. The overlapping quantifiers is 8.6.
8.6.1 and 8.6.2, both are 1 through 20.
When is that?
When is it?
Uh,
It is not until 8.6.1 is November 16th, and 8.6.2 is the 18th.
cool.
Or they're
Yeah.
both on the 16th and 18th.
Okay. So don't stress too much about it. Yeah. I'm just giving examples and parsing them for you for the most part. But long story short, it's kind of weird. I feel like the book should introduce this right up front. But if I say, here's how you parse it. Let's just say I say there exists an x, there exists a y. This is literally just saying there exists an x and there exists a y. Right? If I say universal, and now the book doesn't do it like that, it does it like this. X, Y. I'm just saying for any x and for any y. So it's just making a claim about two things. Does that make sense?
Yeah.
So it's just like, yeah, for anything x variable that you want to plug into x, and for anything y that you can plug into y. Now the tricky part is when you start getting overlapping, like that. And I'm writing this so I don't have to do a bunch of parentheses to differentiate them. But this would say, there exists at least one x, sorry, that's a y, such that for any y, that's how you parse that one. And this would be, for any x, there exists a y. So it's more narrow. It's like, well, for any x, then there is a y. And we'll just have to get good at parsing that. In 8.6. But yeah, don't worry about it for now. When we start doing the proofs, we'll start with the simpler ones. All right, any other questions? All right. So here's the problem. We have this new logical language. We've added onto our old one. And this razor sucks. And we want to be able to do proofs. We know that our old proof rules are going to work, but how do we use them? Okay, let's look at this. Let's say I have an entire proposition, we'll just call it 1. There exists an x such that x has property p. Good? 2. If there exists an x such that x has property p, then there exists a y such that y has property q. This piece of chalk is amazing. I just want to say, it's like so smooth. Anyway, what can I conclude from this?
There exists a y with property q.
Right. Well, how can I conclude that? Modus ponens, right? We're just using our old rule. There exists a y such that y has property q. Why is that? Well, because look, this is just one big proposition. It's just one chunk. Before we would have said just that. I would have been P, that would have been Q, right? So when you have, something like this, just treat that whole proposition as a chunk. It's easy, right? Modus ponens. Get it? Works with any of our 18 rules we have. Questions on that? Here's the problem. I change it slightly. Oh, and look, the lace is nice too. Oh, this chalk. How about I say, for any x, x has px, or x has p. And now let's say for any x, if x has p, then x has q. How do I do a rule on that? Now, what do you think follows from this? Like, just in terms of the meaning. For anything that exists, x has property p, and for anything that exists, if it had p, then it would have q. What follows from that?
And for anything that exists, is property Q.
Exactly. Right. For anything that exists, it has property q. Can you apply a rule to it, though, that we have? That's one big chunk. That's now one big chunk. With modus ponens, I was taking my chunkies and putting them together, right? Well, but now this whole thing is one chunk. Let's just call this square. And this whole thing is one chunk. Let's call it triangle. I don't have a conditional relationship between the chunks. Make sense? But clearly modus ponens works. So how do we get it to work? Well, we could invent, one thing we could do is invent a whole new set of rules. And there would be, I think, at least double or maybe even triple 18 of them. Right? Because I would have to say, neo, or new version of modus ponens. If x, px, and if x, px, then qx, then x, qx, right? Now I'd have to do that same thing for the existential. I would have to do that same thing somehow for multi-parted ones. Because square and triangle aren't going to work now. Because I have quantifiers I'd have to find a whole new way to symbolize all the rules, and I'd have to make one for existentials and for universals, so there's 18 times 2. And then I would have to make them for, well, if we have a mix of existential and universals, so that's at least 18 times 3 more rules. You know what I'm saying? You don't want to do that, right? I don't either. So what the book does, and I think it's brilliant, is it gives you a method. It only adds 4 more rules that allow you to then unlock our 18 rules. Here's how you do it. Okay. The first rule is going to be called universal instantiation. What does it mean to instantiate a universal? Anyone have an idea?
You should take one kind of instance of something that's multiple.
Exactly. So we have a general category, a universal. So let's say we have the general category of being a cat. Right? That's general. It's what philosophers call a one in many. I don't know if you heard me clearly, because my voice sounds echoey to me. A one in many. This one property, being a cat, can be in many cats, right? Many particular things. So it's a universal in that multiple things can share it at the same time, or even across time. And it's an interesting question whether universals exist. That's Plato's whole thing, right? Okay, so if I want to instantiate being a cat, I will point out a particular cat. Right? And I will say this particular cat is an instantiation of the universal property of being a cat. Right? Or if I wanted to say being a mother, right? Who in here is an instance of being a mother? Right? You get it? Are you motherhood itself? No. Maybe. Maybe you're a really good one. I don't know. But you are a particular instance of motherhood, right? Okay. So, yeah.
What's the second word? I couldn't hear you. Universal what?
A universal, so you are an instance of the universal motherhood, or the general category of mothers, right? You're a particular example. So with universal instantiation, what we do is we say, if I have something like x is p, for any x, x is p, I can conclude from that, that A is P. Now A is a particular thing, right? A name. Now I'm not saying we know exactly what A is, but we do know that objects exist in our universe, right? And so I can just say, well, wait, if it's true that anything X is P, that means everything is P, right? No matter what we look at. So then it's safe for me to say, I'm not gonna pick exactly what I'm talking about, but I'm gonna say there's a particular object A that is P. Does that make sense? So for any X has property P, I can say, well, there's some particular object that I'm naming A that has property P. I am instantiating from a universal or a general statement to a particular statement. And I can do this with anything I want, right? Because it applies to everything. So I can point out any particular object and make it part of that. Does that make sense? This is essentially saying all objects that exist, or could exist, are instances of this general property. Anybody think of a property like that?
So for the top part, you could say all things are objects, defining X, defining P, all objects have atoms, then you can just go from there. Cat has atoms, so desk has atoms.
Yeah, good. So if you're a materialist, right, and you say, well, everything that exists is made of atoms, you'd be saying, well, for anything X that exists, X is made of atoms. And then you could list anything that exists, right? Good. Now the question is, are the only things that exist made of atoms? Because we can all talk about general things, right? But general things aren't material. They range over all of us who are material.
Or any physical object, I guess, is better.
Any physical object, yeah. So then you'd have the condition, but yeah. But some people do. I mean, philosophers do. Not so much anymore. They used to think that everything that exists was just made of atoms, right? Atomism. And some people still do. So maybe it's true. I don't know. It's complicated. Anyway, so from XPX, you can conclude that any particular object has that. Okay, so what's this allow us to do? Well, if I now do 3 and I start a proof, I can instantiate 1. And that gets me PA. I can now also instantiate 2, right? What would happen if I instantiate 2 with the letter A? What would it say? PA applies QA. Well, look at that. Now I've got something I can do most ponens on. A is P, if A is P, then A is Q, right? Make sense? So what can I conclude from these two together? QA, right. 3 more modus ponens. So again, what does this say? QA. Right. That's a particular object though, right? Didn't we originally want to say, we know that from this we can draw the conclusion for any X has Q, right? This is particular still. How do we fix that? Any ideas?
Generalization.
Yeah, exactly. So universal generalization is going to do this. It's going to say, if I have, let's say, some instantiated thing, PA, I can draw the conclusion from that for any X has P. Now, hold on a second. I want you to think about this. What's the problem with this rule? There's a massive problem here. Anyone see it? Somebody read this to me and talk about particulars, particular instances. What's this say?
There is a particular A that has property P.
What's this say?
Everything has property P.
How does this imply this?
No.
How does one object having a property P mean all objects do, right? That's bullshit, right? So it's not true. But we need this rule. So here's what we're going to do. We're going to make it true. By putting, you have never seen this before, but a lot of editions, and this book is now getting into it, puts restrictions on using a rule that aren't specified within the rule itself. I do this with the De Morgan's algorithm. Remember I showed you that? I say, look, you can understand De Morgan's this way, or you can understand it more verbally with a description and restrictions of the rule. So we're going to put a restriction on universal generalization. Here's our restriction. This works. Let's just say you can do this only if, well, let's say if and only if A was an instance, well, it's a PA was derived from a universal instantiation, not originating on its own. Okay. That's a complicated description, but it's the only way the rule's going to work.
Can you read that? I can't see it.
Yeah, so the restriction is you can use this rule if and only if A or PA was itself derived from a universal and wasn't asserted on its own. Here, PA was not just occurring in the premises. We only have PA because we started with a universal and instantiated it from there, right? Does that make sense what I'm saying? So that meets this restriction, allowing us to generalize back from QA and PA. What this is doing is, it's basically saying, look, our letters here, A, they weren't names of particular objects that we had in the premises that are already assigned to one particular object. We just want to instantiate like this as a practical tool for being able to use our rules without inventing more. And because we got A from a universal, we can put A back into a universal, right? So the contrast would be this. Let's say I have this set of premises. PA then QA, therefore, for any x, px then qx, right? Or I guess you could start by saying, for any x, px, and then for any x, px then qx. Okay. This is false. This does not work. Because these are in the premises intended to stand for, all I am saying here is it's a particular object. It's already assigned to a particular object A. Right? So the restriction says you can't do anything like this. When you have A occurring on its own, universal generalization doesn't work. Now, if you got A from a general statement, a universal statement, and you're just using the name A to help you break it apart, you're not really taking apart the universal statement. You're just kind of, for your understanding and how we write things, you're just applying this universal statement right here. So if you got the name A, the letter A, by instantiating a universal, then you can extrapolate back out, right? And you can say, for any x, px, that would be 3 universal generalization, right? Because in fact, this is just like, we're just kind of being like, this isn't really doing anything other than playing with the generalization here, right? So we're just going back out from it. And if I wanted to conclude what we originally did for any x, qx, I'd just say 5 universal generalization. Because A, again, A came from the universal. It did not occur on its own. Does that make sense? This is a very complicated rule and restriction. You have to think kind of hard about it. That's why I was saying this is more complicated than anything else that we've done so far. Okay. So let me just show you real quick. I'm going to put the restriction again on the board. So here's universal instantiation. Well, let me say it though. Universal generalization. Restriction R, only use if A was derived from universal generalization, universal instantiation, not occurring on its own. Okay. The book will put it a slightly different way. Read this chapter, and I know probably most of us up until now have maybe read the chapter, but as soon as you get what the chapter's saying, you don't have to read the rest of it, you just do the problems. At least that's how I always did it. I have only read this book once, and it was like a decade ago when I started, when it was still in the 7th edition. And I've never looked at it again since. I just looked at the rules. I remember off the top of my head. So this chapter, when it starts getting into, I believe it's 8.2, read it carefully and really try to understand what it's saying, because it talks about these restrictions. Okay, so I'm going to give you an example. For any x, px, 2, for any y, py, 3, there exists a y such that y is 2, for p, b, 5, pc, then pb. I want to draw some conclusions. Okay, I'm just going to ask you, can I instantiate this? Okay. What's instantiated? Well, I guess that actually isn't a restriction for us, never mind. Let's instantiate this and let's just call it A again, right? 1 universal instantiation. Okay, good. Can I instantiate this? Why?
Because X, Y, and Z all take the same spot.
Right, exactly. Now I could do it with a different letter, I could do it with the same, right? What do you want to do? I instantiate it. What?
Could it be like PB?
Yeah, sure. And that's fine, even though B already occurs, right? Because it just stands for anything, even B. Okay, so we can do two universal instantiations. Okay, what about this? Can I generalize this? Why?
It already exists.
It already exists, right? And just, we're not extrapolating or reasoning from within the universal, right? So I can't instantiate PB. Can I instantiate this? Not same reason, right? They already occur. I'm not deriving it from a universal. Can I instantiate this? Because I got it from universal, right? Let me check real quick exactly the restriction the book says. So to safeguard us, the book is going to say that we technically can't do that because it's already occurred here. It's not that it doesn't work, right? Because we did get this from here, but just to put a safeguard in front of us, the book is going to say, if it already occurred, just be safe and don't do a generalization from it, right? So we can't do that, but we can do this one, right? Because this purely just occurred from instantiating, right? So we can go back and do XPX6, universal generalization. What about this one? What can we do to this? Does anything apply to existential yet? No. Yeah, so we don't have anything for it. Okay. Now here is another safeguard we could put in place. Let's restrict this even more to make it really clear. We're not going to use any particular names now. We're going to now have free variables. We'll have that. And then let's say we have py. Py is now, remember that I reserved x, y, and z for variables? Py is saying that it's a particular object because it's not bound by a variable, right? But it's purely hypothetical. We're not really naming a particular thing now, like A. We're just saying y and keeping it hypothetical. Okay, now this is why we do that. Say we instantiate again px. We want to do that. But we also just have PA up here, or PB or whatever. To be extra safe, we will have another restriction. Only use x, y, z, let's just say y, for instantiating. I'm sorry. For only use x, y, z for instantiating if you want to generalize back from it. We can instantiate any letter we want because it stands for anything. But if we want to unpack something and still keep it supremely general, we are just going to use x, y, or z. So I'm going to instantiate x. Let's just say I instantiate as y. Or I could instantiate just as px, where x is now, a particular thing, but it's just purely hypothetical. I'm still just kind of working within this. I can generalize back out from there, x, px. That's fine. But this prevents me from getting mixed up with the other letters that are occurring. Does that kind of make sense? This is really complicated to explain because you start getting into a little bit of like actual philosophy. Because the whole reason we have these restrictions is because we say, well, you can't conclude from this one thing has this property to everything has this property, right? That's not a logical consideration, though. That's a philosophical one, right? So these restrictions here are pretty complicated, right? Because they're philosophical restrictions. So the book ends up putting it just like this. This is fine, but this is not fine. If you've gotten y by instantiating, and you've kept it supremely general just by saying x, y, or z, you can generalize that back out. But if you have a particular name, especially one that's already occurred, don't generalize from it because you're going to make a mistake eventually. Yeah, I would really say read 8.2 extremely carefully. Okay. Let's do some more examples. I want us to try to make this proof work. All right, look at this proof I just put up with this argument. Premise 1 says, for any x, if x is d or x is v. 2, for any x isn't d. 3, for any x, if x is v, then x is q. Therefore, for any x is q. Does this work? Is this a valid argument? Raise your hand if you think it's valid. Raise your hand if you don't know. I'll tell you off the bat, it's valid. I'm going to walk you through it in English. Look, for anything that exists, it's either going to be D or V. And we know that everything that exists isn't B. Disjunctive syllogism, right? That means for anything that exists, it must be V. Well, if anything is V, then it must be Q. Well, we already know it's V, so anything that exists is V, so anything that exists must be Q. I don't want to invent my new rules, so I can't do it that way, because there'd be too many rules. So I do the instantiation stuff to simplify my rule set. How can I start doing this to unlock the potential with instantiation? What do I want to instantiate?
We want to instantiate the first one.
Sure, let's do the first one. So let's use the supremely general free variable x, y, or z to show by instantiating with x, y, or z, I'm not really pointing to a particular object, I'm keeping it general. I'm just changing the form. So I'll instantiate, let's just say x's without a quantifier. All right, now what?
You can do the same thing in line 2 and get half dx.
Yes. And now I can do it, I can instantiate with anything I want technically, but if I want to get back to a generalization, I'm just going to use the really vague ones, x, y, and z. And I can make it the same x here, right? If I did y, this proof wouldn't work, because now that's a different thing than dx, right? Okay, so not dx. 2 universal instantiation. What do you want to do now?
4, 5 ds.
What?
Would you do 4, 5 ds?
Yeah, 4, 5 dx. What would that get me?
Dx.
Yeah, good. What now? Well, first let me ask, can you generalize from this? Raise your hand if you think yes, you can generalize from this. Raise your hand if you think no. Why do you think no?
Because you took it, I forget like the exact word for it, but you took it out as an example because in the premises it's talking about all of them and you're just giving a specific instance. And you can't make examples out of specific instances.
Okay, so you're close, but I can. Because I am just, when I use my variables, I'm not even really doing a specific instance like with A and B and stuff. I'm just saying, I'm gonna kind of like pretend like this isn't a universal or a general statement. I'm just gonna make it about some vague thing X, right? Now this applies to all the same things because it covers everything that exists. So I'm going to just have X here, but I got these from instantiating them and have kept them general. So because they haven't occurred anywhere else, and I've kept them general with using just free variables, x, y, z, I can instantiate back out. Think of this as not actually saying that a particular object x has not b. When I use these, basically think of these as another way of talking about this. When I instantiate just with x, y, and z, let's say for this one, I'm really just saying anything at all is not B. No particular object, but also any object, is not B. I'm just getting rid of the quantifier. Does that make sense?
But if you like happen to use A, for example, then you wouldn't be able to instantiate.
Then we wouldn't be able to, right. Technically you could, if you only got A from instantiating. But, just as a failsafe, yes. For our purposes, if you get an A or B, anything other than just a free variable, you can't extrapolate back to a general statement. Yeah. I know, this is complicated. This is hard to explain and wrap my head around every time I teach it. So what would happen if I generalized out from this?
It'd be for all x, x is b.
Yes. All right. Now, can I use this with this to do my exponents? No, so that didn't really help me. So what can I do?
Instantiate line 3.
Good. And I'll get Vx, then Qx. Now what do I do?
Use both exponents to get QX.
So 6, 8, Qx. What's my final step?
To generalize.
To generalize for any x, Qx. Yeah. Universal generalization from that. Now here's why it works in an argument form. Everything here has been supremely general, applies to everything that exists. Everything I've done here, I'm not talking about particular things. I'm just giving a variable where you could plug anything into this that you want, and it works. So for anything we plug in here, anything at all, this argument's going to work, right? Well, therefore, because I've kept it supremely general, you can plug anything into the x slot here. I can now conclude that the conclusion that follows applies to everything. Now that philosophically makes sense. But if I was just going from particular cases to universal statements, that doesn't make any sense, right? So everything we've done here has been completely general. Just with a particular form. Right? This is just a way of writing to get our written symbolic system to work easily, but philosophically, this is still completely just general.
I just can't see it. Would the rule for 10 be 9 UG?
Yeah, 9 UG, sorry, yeah, right.
There you
Okay. Questions? Read 8.2, really carefully. What time is it? Anybody got time?
It's 11:17.
What time do we get out?
45.
40, yeah. All right. Well, I'm sorry to do this to you. There's 2 more rules, and they have the same bullshit restrictions. They're really complicated. We've got our universal rules that help us do proofs. But what about our existential rules? We have to have something for existential quantifiers. Well, similarly, we have existential, I'm going to do this in reverse order, existential generalization. Okay, this one makes a lot of intuitive sense. Let's just say I have knowledge that some particular A has property P. This thing A has P. What can I conclude from that?
There exists an A that has property.
Yeah, except we're going to keep it general. We're not going to say there exists an A. We're going to say there exists an X, such that X has P. Because A is a name for a particular object, right? Good. You see how that works? If I have a particular taste of something, I can then generalize and say, well, it's basically like I'm talking about it without naming it. There exists an A such that A is wearing a purple shirt. Well, sorry, I'm going to start over. This particular thing A is wearing a purple shirt. I could just say, there exists something out there that's wearing a purple shirt, right? Okay. So generalization's easy. There's no real restrictions on that one. Here's where it gets tricky. Existential instantiation. Let's say I have this. There exists an X such that if X is P, then X is Q. A is P. Am I able to conclude that A is Q? Why not?
Because I read 8.2 and it says that you can't use instances already in the problem.
Okay, good,
Use,
yeah.
instantiation.
So with existential instantiation, the restriction we're going to put on is you can't do this, something like this, because you can't instantiate to a name that already exists. Okay, but why? Why doesn't this work philosophically?
Because we don't know that A is the one that exists.
Beautiful. Exactly. Look, this premise one says there is at least one thing that if it was P, then it was Q, right? Am I telling you what that thing is? Am I telling you there's only one thing? I'm telling you there's at least one, maybe there's a million, maybe there's 2, maybe there's 5, right? We don't know what they are. Well, here I'm telling you A has P. Does that mean that this A is the thing that if it was P, it would be Q? We can't conclude that, we just don't know, right? It's just indeterminate. It's like saying there's someone out there who, if they got COVID, they would die. Let's say I get COVID. Does that mean I'm the person that's going to die? Not necessarily. I mean, maybe for me, really, yeah, unless I run a stupid Bayes math. But does that make sense why you can't draw that from there? Okay, so how could we do this? We just can't conclude that from this argument. So the restriction, the form of existential instantiation goes like this. If I have a general existential, I can conclude that, let's just say some A, some particular named object fits into that. Now, my restriction R is that the letter I instantiate with can't already occur in the premises, or anywhere, really. I can't even use the same letter that I got from any inferences. I have to use a completely new letter whenever I instantiate. Why is that? Again, let's say I have this. There exists an X such that either X is P or X is Q. I already know up here that, let's just say B is my father, a dad, okay? Think about this. There exists an X such that X is, I don't know, X is into grilling or X is into building decks. B is a dad. Can I conclude anything from that with my rules? What if I added in for any X's, if X is a dad, then yeah. Can I conclude anything from that now? I still can't. And if we have to, like, these restrictions make us really think. Okay, so I'm going to say, likes building decks, likes grilling, sure, whatever. This is a dad, right? Now, I can get this, sorry, I'm writing a slant. 1, 2, 3. Wow, that's really slanted. Sorry. If I say for any X, if X is D, then X is not Q, I can instantiate that, right? Universal. So let's say, I'll try to stop writing a slant. I can make it about B, right? Because of the particular object, and I want to get it to line up, right? So that's 3 universal instantiation. Now I can do modus ponens, right? And I now know that this guy B, or whatever, doesn't like grilling. He's a dad, but he doesn't like grilling. Now let's just combine these two, 5 and 1. This one says, there exists an X such that X either likes building decks or X likes grilling. Mr. B doesn't like grilling. Can I conclude from that he likes building decks? No, because we do not know if this thing we're talking about is Mr. B. Right? Does that make sense? Okay.
Good question.
Uh-huh.
I thought we couldn't use if it was already part of the equation. So how could we use B on 4 if it was already on 2?
You can instantiate B because, like, this any X is PX applies to anything, right?
Okay.
You just can't, if you do a particular name, you can't get back from that to a generalization. Does that make sense?
Yeah.
Yeah. And that's why the book really shows you can't do it with an A, but you can do it with a Y, right? Okay. So restrictions, they're kind of like the opposite of each other. Universal instantiation doesn't really have any restrictions. But universal generalization has a big-ass restriction that's philosophically dense. Existential generalization doesn't have a restriction. But existential instantiation has a big restriction, right? You have to pick a new name that hasn't occurred anywhere to be extra safe, right? That you're not assuming that two different things are actually one thing. That's why I teach them out of order. They're kind of like mirrors of each other. And this should show you, I've said we're going to keep metaphysics and stuff out of logic as much as possible, because that would require us, in order to know how to reason, we'd have to do all this metaphysics, right? This is the one time we make an exception. We know the basics of metaphysics. You can't say, you know, this particular thing has this property, so everything in the world has this property, right? That might sound like obvious to everybody, but that's a metaphysical claim about how reality works. Let's say that you actually believe, like a lot of people do, if they're Hindu or sometimes a Buddhist, that really in reality there only exists one thing, the world. And you're just parts of the world, right? But you're not really individuals, you're just part of the world, right? Well, do you see how in that metaphysics you might be able to make the case that if a part of the world has a property, then in some sense the whole world has a property? Yeah. Now maybe that doesn't work, but monism meaning there really only exists one monad, one thing. You know, they might have some problems with certain applications of these restrictions. So this is a philosophically, actually, like, this system has to be built more philosophically, if that makes sense. No way around it. And it's complex too, because what if you say this, look, doesn't it kind of make sense to think that if, oh man, what would it be? Let's say that some of your liver has cancer. You have liver cancer. Doesn't that mean you have liver cancer? Your entire liver has liver cancer? Right? So again, we're saying that's just a way of talking. If part of your liver has cancer, it doesn't mean your whole liver has cancer. It doesn't mean there's cancer in your liver, right? So again, even some of the ways of talking, we'd have to rephrase with these restrictions, if that makes sense. Okay. Rapid fire. What's it say?
There exists an x that x is p and x is q. Or a is q? Oh,
Mhm.
I don't know.
So the quantifier doesn't range over this, right? It's just attached. The quantifier ranges over this, but it's saying, well, A is Q. That particular thing is A is Q. But there exists an X such that X is P. The other way you could put this, that's less ambiguous, is like that, right? Okay. Is this an okay move? Can I do that with an existential instantiation? Why?
Because it already exists.
Right, A already exists. It's a big ass assumption to think this one thing we're talking about that's P is the same thing as A that's Q, right? Okay, good. So we can't do that. Can I do this with existential instantiation? Why?
Because B is just, we don't know what B necessarily is, but we know that we're just saying that this is the thing that exists as P.
Yeah, and we could just pick the name B for it, right? It's like if I'm like, You know, I don't know exactly who I'm talking about, but I'm going to pick the name. Let's just say, I know somebody's in the library right now. There exists somebody in the library. I'm just going to name that person Beef Boy. And then I can say Beef Boy's in the library, and I'm right? Because I'm not talking about a particular Beef Boy, I'm talking about a particular object, but I'm not telling you which particular object I'm talking about. So Beef Boy could be anyone, a boy or girl or anything, right? Like in the library. Any person. Okay, so if I have that, can I then do this? With universal generalization? No, why? Is this okay to do? Instantiate from there. But is this side okay from here? Why not?
You're going from like one case to a general. You're saying everything Q, everything X would be Q, and that's not.
Good. Where's my recipe? Okay. What if I had that together? What's this say?
For any X, X is property Q, and there exists an X such that X is property Q.
Okay, good. If I did this, is that okay if I instantiate this with A? Yep, because this applies to anything, right? Is it okay if I now do this? Why not? That's existential instantiation. Why can't I do that?
Already used A.
I already used A, right? So let's just follow the restriction, right? What if I did this, though? Is that okay with the existential instantiation? Why?
Because A is just the arbitrary thing that exists, and that's property Q X.
Exactly, right. Now what about this? If I went, that's okay with existential instantiation on 1, call that 1. Can I do this too? Universal instantiation? Yeah. Right. Why?
Because everything has property Q.
Yeah. So it's a safe assumption to say A, even if we already have an A, has it too. Yeah. Okay, what about now I want to extrapolate back with a universal generalization. Is that okay? I see Samantha, you shake your head.
I said no.
Okay, why not?
Because you can't do particular to general.
Right, you can't do a particular to a general unless it's X, Y, or Z, in which case those aren't really particulars, right? They're just a way of writing the general statement. Okay, so that doesn't work. What about instead before I keep it QA, and let's say, I suppose, existential generalization, is that okay? Yeah, that's okay. I'm just extrapolating from this particular thing I know exists, right? Back to, there is something that exists that, oh, I'm sorry, I did it as QX, QX. Okay, there we go. Right? So, as you can see, you can kind of get disparate things and infer from them a unified proposition, like that. I know this is complicated, And like half the class right now is watching this online, and they're probably going like, oh shit, what the hell? Like, what's going on, right? Yeah, this is complicated stuff. Any questions on any of this? Okay. What time is it now? 11:36.
Is that a negation on two?
Yeah, that's a negation right there. Okay. So just a note, I've already kind of talked about this, but if you have multiple existential claims like that, even though they're both using the variable x, you cannot assume they're talking about the same thing, right? There is one thing that's p, there is at least one thing that's b. That doesn't mean I'm talking about the same thing, right? Okay, just to clarify. That's why these restrictions are in place, ultimately. These more complex problems than that arise, but they're fundamentally the same thing, the same issue. How do I prove this conclusion? First, let's see if it's valid. Somebody read the argument to me.
For any x, x has property p, or x has property q and x has property t.
Good.
There exists an x such that not x is property q and x is property t. And 3 is for any x, if x is property p, then x is property e.
Good.
Then the conclusion is that there exists an x such that x is property p.
Okay. Raise your hand if you think that argument is valid. Raise your hand if you're not sure. Okay, you think it's valid. It makes sense in English, right? Especially if we were to not just talk about, V and P, if we were to give them actual property names. But let's prove it with our rules that it's valid. How can I do it?
Did you instantiate 2 first?
Sure. Let's go to existential instantiation. What do you want me to instantiate it as?
Can you do just x? Is that allowed?
Not with existential.
Not with
Remember
existential?
that x, y, and z are going to be general still. I mean, I guess you technically could. It's just kind of an arbitrary fail-safe, right?
A?
Yeah, let's pick A. And remember, why can't I write 5s anymore? Remember that this single variable quantifier is ranging over the entire thing. This is talking about one thing, right? There is at least one thing that this isn't true of. Okay, so we can have A here. Right now, what do we want to do?
Instantiate 1.
Okay, what do you want to instantiate 1 with? That'll be universal instantiation, right? What do you want to do with that?
You use a.
We could use A again, right? Because that applies to everything that exists. So I can just say it applies to this A. Now that I did that, what could I not do with it? What does this prevent me from doing now that I instantiated with a particular letter?
Generalizing?
Yeah, I can't generalize back out. I'm done now with generalizing. I can't do it. Okay. So 6. What can I do from there?
You can do p at least.
I get PA from 4, 5 destructive syllogisms. What from there? Hmm?
Would you need to universal 3?
Yeah, so 3 universal instantiation? Yeah, what would I do for that one?
Could you use A?
Yeah, yeah, because it just applies to everything.
And then
What?
MP. So
MP,
it'd
yeah.
be 6, 7, MP. And that'll give you BA.
Conclusion? How can I get to that from this?
Can you generalize it?
With an existential,
So,
right?
Yeah.
Yeah.
So EG.
So it would be EG.
That's what I said.
Oh, okay,
Sorry.
So EG, existential, generalization, right? And that makes sense because I know this particular object V has V, so there is at least one thing that has V. Boom. You see why we need these weird rules with restrictions? Again, we could invent a whole new set of rules, and some people do. And some people's logic books don't teach you propositional logic anymore because they think it's obsolete. They just teach you this. And so they have their own rules, like modus ponens for this. But then they have a lot more rules, like I was saying. So this lets us now we know propositional logic and can model things in terms of propositions. And we know predicate language, and we know how to do proofs in them. And all we had to do to learn 2 languages in one class is just to add these 4 rules, even though they're kind of complicated. It's a lot better to know both kinds of logic. Because this is only a recent invention. If you want to read philosophy or anything prior to mid-20th century, like 1950s, 1960s, you're not going to ever see this. At most, you're going to see propositional stuff. So historically, if you're interested in philosophy or anything, I mean, or even just general history of things, you'll have to know propositional logic, at least the basics too. Because again, propositional logic was developed likely before we have written documents of like philosophical record. Because you could see Aristotle, so you can see Aristotle actually has a system of predicate logic already. That's a long ass time ago, right? Thousands of years. But Aristotle also, there was before him, the Pythagoreans were trying to make philosophy like geometry, and they very likely had some sort of logical system that was like propositional logic. But then the Stoic ancient Greek philosophers actually literally already developed basically everything we learned about propositional logic. They did that thousands of years ago too. So if you look back in the record, you kind of have all the systems in their infancy, but really propositional logic was the one people went with all up through the Middle Ages, and then it wasn't really until the last 200 years in England and the United States that we started developing this stuff. Right? So yeah, that's why we kind of teach you both of them. Any questions? Okay, I know this class is probably like a headache or something, but all right, I'll see everybody later. Don't fall behind, we're almost out of the woods. Also, congratulations everybody, you have now learned 2 full logical languages, and we're done. We're just practicing, and we're done for the semester. All right, see you everybody.